What happens when you shoot down the leader of a drone swarm? Nothing. The rest don't crash. They don't panic. They don't even slow down. Because here's the truth most people don't know. Drone swarms don't have leaders. Instead, they operate like a living organism, where every single drone is part of a shared digital brain powered by geometry, mathematics, and decentralized communication networks. And today, with new counter-drone systems being revealed, understanding how swarms actually talk is more important than ever. When most people imagine drones, they picture one pilot controlling one aircraft. Maybe two, maybe five. But military-grade drone swarms work very differently. Instead of centralized control, they use something called a mobile ad hoc network, or MANET. And combined with a geometric concept called Delaunay triangulation, these drones become capable of coordinating, adapting, and surviving even under attack. Today, we're breaking down exactly how that works. Let's start by destroying a common myth. There is no master drone controlling the swarm. If there were, it would be a massive weakness. Destroy the leader, and the entire system collapses. Instead, swarm drones operate using distributed intelligence. Think about a flock of birds or a school of fish. There's no commander telling them where to move. Each individual only follows simple rules. Stay close to neighbors. Avoid collisions. Move toward shared targets. But when thousands of individuals follow those simple rules, something powerful emerges. Collective intelligence. Drone swarms replicate this exact biological principle, except they use wireless communication and algorithms instead of instinct. Now let's talk about the technology that allows drones to communicate without relying on a central control tower. This is where mobile ad hoc networks, or MANETs, come in. A MANET is a network that builds itself automatically. There is no fixed router, no base station, no permanent infrastructure. Every drone acts as both a device and a relay station. Imagine passing messages across a crowd by whispering to the person next to you, who then whispers to someone else, and so on. That's exactly how swarm communication works. Each drone constantly shares position data, speed and direction, environmental sensor information, mission updates. And because every drone is connected to multiple neighbors, the network becomes incredibly resilient. If one drone disappears, the data simply reroutes through other drones instantly. The swarm never loses awareness. This is why removing a single drone rarely disables the entire group. Now here's where things get fascinating. Communication alone isn't enough. Swarms must also maintain formation, spacing, and awareness of their surroundings. That's where Delaunay triangulation enters the picture. At its core, this is a mathematical method that connects points into triangles in the most efficient way possible. In swarm engineering, each drone is treated as a moving point in space. The triangulation algorithm connects drones to their closest neighbors, forming a constantly updating triangular mesh. Why triangles? Because triangles are extremely stable geometric structures. They allow drones to maintain optimal spacing, avoid collisions, cover maximum surveillance area, adapt instantly when a drone disappears. If one drone is removed from the network, the triangle mesh simply reshapes itself. It's similar to how spider webs redistribute tension when one strand breaks. The swarm doesn't fall apart. It reorganizes. Here's where swarm technology begins to feel almost alive. Each drone runs algorithms that analyze neighbor behavior, mission objectives, environmental threats. Instead of waiting for commands, drones vote through shared data. If multiple drones detect an obstacle, the swarm collectively reroutes. If part of the swarm loses communication, nearby drones automatically adjust formation. This decentralized decision-making makes swarm systems incredibly fast and difficult to disrupt. Because there is no single brain. The brain exists everywhere. Modern counter-drone technology is improving rapidly, but swarm engineering introduces a new challenge. Traditional defense systems are built to eliminate individual aerial threats. But swarms behave differently, even if several drones are neutralized. The MANET network reroutes communication. The triangulation mesh reforms. The mission logic redistributes across surviving drones. It's similar to cutting off one branch of a tree, the organism still survives. That's why new defensive technologies are focusing on disrupting communication signals, overloading swarm coordination, interfering with navigation algorithms. Because breaking the swarm's communication is often more effective than targeting individual drones. Drone swarm engineering is still evolving. Future developments are exploring AI-driven adaptive formations, autonomous target recognition, self-repairing communication networks, cross-swarm coordination between air, land, and sea systems. Some researchers are even experimenting with swarms that can learn and improve performance during missions. Which means future swarms may not just follow rules. They may create new ones. Drone swarms don't operate like machines. They operate like ecosystems, built on wireless mesh communication, driven by geometric stability, and powered by decentralized intelligence. They represent one of the biggest shifts in modern engineering and autonomous systems. And as both swarm technology and counter-swarm systems evolve, the battlefield, and possibly civilian technology, may be shaped by this invisible digital conversation happening in the sky.